You know, when you think of a black hole, you probably picture this cosmic vacuum cleaner, right? Just sucking up everything in its path. But what if that's not the whole story? What if there's something way, way more profound? What if black holes are actually the universe's ultimate laboratories, holding the keys to its deepest, darkest secrets?
And that is exactly what we're going to dive into today. We're going to see how scientists are using these incredible objects, from the ones that exist only in theory to the ones that are terrifyingly real, to probe the very nature of reality itself. We're talking about the fabric of space-time, the hunt for new particles, the whole shebang.
All right, let's start at the deepest, most mind-bending frontier you can imagine, pure theory. We're going right to the edge of a black hole, to the event horizon. This is the place where the laws of gravity and the laws of quantum mechanics don't just, meet up for coffee. Oh no, they collide, and it creates this spectacular, unresolved puzzle.
So, the first big piece of this puzzle comes from the one and only Stephen Hawking. He figured out that black holes aren't totally black after all. They actually glow, with something we now call Hawking radiation. But here's the really weird part. It isn't that they glow that's so strange, it's how they glow. The radiation is what scientists call perfectly thermal, which basically means it's totally random, like heat. And that is just bizarre. It hints at some hidden, secret connection between the smooth, predictable universe of gravity and the wild, chaotic world of quantum physics. And honestly, it's a connection we still just do not understand.
So how on earth does this strange glow even happen? Well, the leading theory involves one of the weirdest ideas in all of physics: quantum entanglement. Okay, think of it like this. Imagine you have a pair of gloves. You put each one in a separate box and mail them to opposite ends of the universe. The second you open your box and see a left-handed glove, you instantly, and I mean instantly, know the other one is a right-handed glove. Entangled particles are just like that. They're linked in this spooky way that just completely defies our everyday logic.
And this is where the mystery really gets deep. The theory goes that Hawking radiation is made of these little entangled pairs of particles, popping into existence right at the event horizon. Now, one of those particles manages to escape, and that's the radiation we could one day see. But its poor partner, it falls into the black hole, gone forever. So this raises a massive question. What happens to that quantum link, that entanglement, when one half of the pair crosses the point of no return?
Well, according to some fascinating research by Schitzhold and Unruh, there are basically two big ideas on the table. Theory A says those quantum connections were always there, just hanging out in the vacuum of space, piling up at the horizon for eons, just waiting to be revealed. But Theory B, it paints a much more exciting picture. What if the black hole itself is actively creating this entanglement, forging these linked pairs in the violent chaos at its edge? So, is the black hole a librarian, just revealing what's already there? Or is it a factory, building something new? The answer could completely rewrite physics as we know it.
Okay, so let's pull back from the world of pure theory for a second and talk about the real universe. I mean, it's one thing to have these beautiful, complicated ideas, but how could you ever hope to test something so strange? Well, what if the universe has already built the giant experiments we need?
This quote from Professor Joseph Silk just nails it. Instead of us trying to build bigger and bigger machines right here on Earth, physicists are starting to look out into the cosmos, specifically at those supermassive black holes sitting right in the heart of nearly every galaxy.
So, how does this cosmic supercollider actually work? Well, it's a four-step process. Step 1. Gas and other particles get pulled in, starting their plunge towards the black hole. Step 2. The black hole's insane gravity revs them up, accelerating them to almost the speed of light. Step 3. Right near the event horizon, they smash into each other in a collision of unbelievable force. And finally, Step 4. Not everything falls in. Some of the debris from that collision gets shot back out into space, carrying the evidence with it.
And what might these cosmic smash-ups create? Well, potentially the biggest prize in all of modern physics: dark matter. You see, the absolutely extreme conditions near a supermassive black hole could be the perfect furnace to forge these mysterious particles, the stuff we think makes up most of the matter in the universe, but we've never, ever seen it directly. And you want to know the best part? We're already on the lookout. Amazing observatories like IceCube at the South Pole and KM3Net deep under the Mediterranean Sea are designed specifically to spot these super high-energy particles zipping in from space. A weird signal in one of those detectors? That could be our very first sign of a brand new particle, created in the heart of a black hole supercollider.
Okay, but what if we didn't have to look light years away? What if, and this is going to sound crazy,
What if we could create a black hole right here on Earth? I know it sounds like something straight out of science fiction, but for particle physicists, it's a very real and, let me tell you, a very exciting possibility.
Okay, so here's the thinking. Some theories of gravity suggest that there are more than just the three spatial dimensions we know and love. And if these tiny, curled-up extra dimensions are real, they could make gravity way, way stronger at very small scales. So strong, in fact, that smashing particles together at a place like the Large Hadron Collider might just concentrate enough energy into a tiny enough space to pop a microscopic black hole into existence.
Now, before you start to worry, these things would be totally harmless. They'd evaporate in an instant. But so far, the search has turned up empty. Experiments at the LHC have pretty much ruled out creating micro-black holes with masses below a certain energy range, about 4.3 to 6.2 tera-electron volts. To put that in perspective, that's trillions of times the energy of the light you can see. So yeah, that sets a pretty high bar, but it definitely doesn't mean it's impossible. It just makes the hunt that much more interesting.
In fact, some physicists are starting to think we might be looking at this whole thing the wrong way. Maybe the problem isn't that we don't have enough energy. Maybe the problem is our understanding of how quantum mechanics actually governs their creation in the first place.
So let me introduce you to a new idea called Horizon Quantum Mechanics, or HQM for short. It suggests that creating a black hole isn't like flicking a light switch. It's not an on or off thing that just happens once you hit a certain energy level. No, it's actually much more like a dimmer switch.
So let's just break down the key difference here. The standard model assumes this sharp cutoff. Below a certain energy, no black hole for you. Above it, you can make one. But HQM says it's all about probability. Any particle collision has a chance of forming a black hole. It's just that the chance is ridiculously small at lower energies, and then it smoothly ramps up as the energy increases.
And here's why that is so important. This HQM model predicts that if the LHC is making tiny black holes, they are probably being created at lower masses than what we've been searching for. They're just being created very, very rarely, which means our current search methods might be missing them entirely. We might be out there looking for a giant floodlight, when really we should be trying to spot a tiny flicker.
So when you put it all together, what you have are these three incredible, parallel frontiers all pushing at the same fundamental questions. You've got the quantum theorists asking what happens at the edge, the astronomers using the entire cosmos as their personal particle collider, and the physicists right here on Earth trying to build these exotic objects from scratch.
So what's the big takeaway here? It's that black holes are no longer just these passive dead ends of stars. They are active, dynamic laboratories for physics. From the deep quantum puzzle of entanglement, to the colossal cosmic collisions that might finally show us dark matter, to the mind-bendingly probabilistic chance of making one on Earth, black holes are right at the center of our quest to figure out how the universe really works.
So, the next time you look up at the night sky, don't think of black holes as just empty voids. Think of them as beacons, lighting the way forward. They truly represent the edge of what we know. And by studying them, both way out there in the cosmos and right here in our labs, we are asking the biggest questions we can possibly ask. The only real question left is, what are they going to show us next?